So,
What would be, how would I write
let's get
these
ready to
terms?
roll here. Big day today. Definition of the integral, formal definition of the integral.
What'd you
We'll
say?
have to do for Monday.
I plus 1 over 2. It's just very easy. I mean, look at the top numbers. The top numbers are changing. That's where the I will get involved, right? Anything that's changing, that's where you want the I, because the I is changing. The I is going to be a 1, then a 2, then a 3, right? Well,
Going to be,
the top is always 1 bigger than what I is.
anyway.
But the bottom never changes, so the bottom stays at 2. Now, what is the top number on this going to be? What's the top number on
On
this?
the first 6.
7, right? Because 7 plus 1 is 8. But do you see how that was much easier to write if I wrote it out a certain way?
Midpoints.
Okay? Now, some people often look at this one and do this. They say, well, why not start your I at 2?
Spring break.
Then what would be inside? Then it would just be I over 2. And then let your sigma go from 2 to...
Be plotting a bunch of points,
8.
drawing rectangles.
And if somebody really wanted to be a smart aleck, they could start their I at 3.
Some will be right, some will be midpoint.
And then what would this be?
And so and on the next quiz that we take,
And go to...
which will be next week, actually, because we got kind of straight.
How many different sigmas can we write for this?
Wednesday, no class, and then I'm going to be going
Infinite. We
Friday.
can sit here and write them all day long.
Just gonna be kind of a-
We usually like to start I at 1. Just makes it simple, but you don't have to, right? And you could, sometimes it's easier to write the sigma if you start it somewhere else. So it's totally up to you, right?
But
If you're
anyway,
doing it, but a lot of
we're
times
doing
you start
that.
at 1.
And then,
Okay, so the lesson on that one is, number 1, there's infinite number of sigmas that can all represent the same thing. But also, number 2, the way you write your sum, and I'll go back to this, when I said the other day, you know, you guys are going to think it's busy work when I'm making you write this all out, but it's really not busy work. It's writing it so we can see a pattern. That's what we're doing. And it's because of this that we want to do. Okay, so here we go. So,
the width of our rectangle.
Okay.
So,
All right.
we know
So,
that if we go from
here's
here
what we're
to
going to
here,
do. We're going to
go
start
by
with the
2s.
integral 0 to
Okay.
pi. So I'm going to start a new
6
page
points,
in your notes,
give us
whatever, but
5
this is connected. This is going to be,
And then
this is
we
going to
get
be the big
midpoint, we
deal
go in the
here.
middle,
Now,
and we draw
you're going to have to
our height
try to
right
stay
there.
with me and
So
stop me
here
if you
in the
need
middle
to.
of these
But it's easy to get lost in the weeds because we're going to write out a bunch of stuff here.
Okay,
Okay, but what are we trying to
I
do?
go over
We're trying
this
to
way.
write,
and then down, and there's.
well, what we want to do is
midpoint.
find the integral
And then I
from
go
0
to the
to
middle,
pi,
right
that's
here,
where
and
the
then
x.
that
So we
way,
already
that
know
way.
that that's
There's
this piece
the
of area right
rectangle.
here.
And then I go to
It's all
the middle,
talk where you get to
down
write this
here,
out.
go that
We
way.
want this piece of area.
Go
We
that
know
way.
by the fundamental theorem that that's 1/3 x cubed,
And we
from
draw
0 to pi, so we put a pi in, we
Getting
put
a
pi
midpoint
cubed for 0
rectangle, then
to
of course
0.
you're supposed to.
So we know the area is going to be pi
I
cubed
want
over
you to
2.
use that
We know that's the area.
notation, so this would be what, 1.
Okay, but remember, the whole point of this is there are some
Times 2.
functions that don't have antiderivatives.
2.
So we have to
What's
do
the first
approximations.
one?
We have to do right
And
rectangles.
you know
4
what
right
the
rectangles
X is
not
now
going to be
again.
a very good approximation. 100 would be better, 1,000 would be better.
Is
Okay.
because of where we're
Infinite would be the
headed with
best.
this.
That's where we want to head
It's
to.
about patterns. I mean, I
We want to
realize
see how we
saying
can
all
do
that
an
to you,
infinite number of
what you
rectangles.
do.
But
I
we're
want
going to
you
need
look at
this
and
notation,
look
the
at
sigma
that first
notation stuff.
Left edges or the first
Okay, that's
right
where we're going. So let's start with 4, because we can have.
And you know what delta x is, and you know
Okay,
everyone.
so let's
else,
do
and that's
4
gonna
right
go
rectangles. So,
by the
what do I do
width by
first?
1 width. Delta x can go by 2. So we know that this
divide it up into 4 parts, right? What's my delta x going to
The
be?
next one's going to be g of 2, and you can write these out.
Pi minus 0 over
4, and then you can get those
4.
values.
So it's going to be pi 4s, right?
To that, okay?
So, let's come over here and let's divide this up into
What was
4s.
the one you had to do trapezoid? 4.
So what's my first one going to
And that
be?
was from what to what? Still
Pi
5
fours.
to 5?
What's my second one going to be? Pi halves? No, did you guys not learn a thing?
Our total width, our delta x is still
2
going to
pi
be 2,
4s.
because we've got that.
I want to see the
same,
pattern. Don't write it like this.
same
Write it
width.
like
We
this.
still have 5
Right?
of them. But the
Yes.
difference on a trapezoid, of
Good.
course,
No, I
is
expect
we
you to
take
say pi
the
halves.
left edge and we take
All right.
the right edge. Now, so what was interesting.
2 pi 4s. What's the next one?
I think of all of the 5.
3 pi 4s. What's the next one? 4 pi 4s. Exactly.
I mean,
Yes.
because this one
That's
is just
going to
really
make
two
it much
triangles,
nicer for us to
right?
write
This
it
first
that
one
way.
here is.
Okay, so we're dividing it up into 4. So what's my first right edge, Emily? What's my first right edge?
1/2 g of negative
No.
5 plus g of negative 3
Where's this
And then
integral
times
start?
the width of 2.
Starts at
It just so
0.
happens
So the
that
first
geometry
right
goes
edge,
negative, and this one goes
so I
positive.
should put a mark here and I should put a mark here. Remember, to do 4 subintervals, you need 5 marks,
It's kind
right?
of interesting
So my
that
first
the
right
trapezoid
edge
formula
is pi 4. So if I was actually going to draw a right rectangle here,
in this
it
case,
would look
two
like that.
circles,
And then it would look
which
like that.
you wouldn't even
And then it would
hold
look like that,
shape, I
right?
don't think,
But
in
we don't need
geometry
those,
to
we don't need them.
trapezoid.
So what am I gonna write here?
But for our purposes, it is, okay, because it's
F
the
of
sum that we care about, so we're calling it the
5/4, this is why we did that homework yesterday, right? So we could do this, times
Here,
5/4
this one, I think is the only one
plus
that's actually a trap, oops, that one went to there, that was actually a
F
trapezoid.
of 2
is
pi
that
fours
one right there. And that's
times
when you have 1/2, and again, you get the
pi
pattern.
fours
You don't use this
plus
one, but,
F of
the left one, but the other ones you
3
use
pi
twice,
fours
so you're gonna use that -3 twice.
times
It's the right edge.
pi
of the
fours,
first half, so
and then
it's the left
plus
edge of the second
F
half.
of
And then this one just becomes.
4
this one
pi
just is
fours,
a
we go to the
triangle.
right, last
Okay,
right
again, it
edge,
doesn't matter.
times pi
Just
fours, that's
show
4
that
right
out.
rectangles.
Where we wanna get
Now,
to here.
look at
is-
that.
And we'll do
We
that
can
today.
write a sigma
Where we
for
write
that
these
because
out,
we got a
these
nice
out, how do you draw
pattern.
the Pictures, which is what you did on
We
7.
can now
And-
simplify that sum.
happens
Anytime we have an
drawn
expanded
pictures
sum,
along
we
this
write it
picture,
as a sigma. That's what we were doing
picture,
back here.
it
We
will
just
help
did that
you
here,
write
right?
it
We
out.
got a sum, we
But
can
I
write a
would
sigma, so we
this
can write a
right
sum.
here,
So,
This
we're gonna
right
start
here
our I
would
of
be the
1.
same, no matter what that graph
And what
looks
would
like,
be
no matter
inside
what
here?
the G function is. That's why I like writing it out that way.
The only
It doesn't
thing
matter
that's
what the function
changing
is when
is
you
the
come in.
top number,
The fact
right?
is, and we can figure out what's G of negative
1 pi, 2 pi, 3 pi, 4
Okay.
pi, isn't that what
The next
I
one
is? So
would
it's
be
gonna be
right
that
here.
I pi?
Would be that trapezoid. So that's
Isn't that what it's
G of
gonna be?
1
But it's gonna be F of
plus G of 3. Okay, times
I
2,
pi
and then the
over
last one
4
is right there,
times
and that's G of 3. And we go
pi
all the way
over
to
4,
the
right?
edge.
Isn't that give us each term? And then the
We
top
use
number on the sigma
-5
is,
one time, the other
4.
one.
so I will be a 1, this will be
So
F
that's
of pi
what
4.
we'll
So
find
I will be
out.
a 2, it'll be F of 2 pi 4. So I'll be a 3, it'll be F of
Okay.
3 pi 4, and
Alright.
so on. Right?
So
See how
I'm
easy
gonna
that
talk
was?
about 7.
Because in every one of these terms, each term's exactly the same except for that top number. 1 pi, 2 pi, 3 pi, 4 pi, so it'll be I pi.
So as soon as, so this one gets us to where we can, you did
Well,
have.
we're gonna do that right now.
Right?
Yeah,
So
oh, I see what you
it
said,
doesn't
yeah.
really matter even what
F
this
is always
picture
gonna be
looks
that.
like, and I can
So
still
F
do
is
it,
the X
but we're
squared,
going
right? So
here
that's
to
what I
here.
want to do next. Remember I said I always want to do this in F notation
So
first?
7 minus 1
Now
times
let's take
3.
it out of F notation,
So these are gonna be
and let's
two
put it
Y's,
into the
we're gonna
function.
have
But remember
there,
German
we're
short
gonna have
hair?
there.
What's F, right?
And what
If
you're
this
gonna
is F of
notice
X,
today
X squared.
is
What's
I
F
go
of A?
Is really all I care about is this, the X
A squared. What's F of German short hair?
Most about.
German short hair squared. So what's F of I pi
write
force?
this out without even drawing the right rectangle.
That's
All I'm
I
gonna be
pi
looking at is
force
X-axis.
squared,
Okay, so I know I'm going
Times
to do
pi
7. I know
force.
I'm gonna have 3 subintervals.
right?
And so where is my first right edge? What
Okay,
function?
now.
F, okay? So
What?
where's my first right edge?
The function,
Where?
F of I, this is F right here, X squared.
3.
So F of I
So my
pi
height
force
is
means
going to
take
be
I pi force and plug it into the
F
function.
of 3.
Okay.
And what's my width?
Well, I want you
2, right? Plus my next right.
to do this for me, do pi force.
Why's it gotta be an F
So
of
let's
I?
take each
Because
one of
the
these
width
and
is
plug it into the function.
2.
So do
right?
pi
Because I
force
start at
squared.
3, so if you know where
Okay,
you start.
Tim, you back him up on that.
1 to
Do
7,
pi
that's
force
1
squared
to
times
7.
pi
If
force,
I go by 2,
plus
my
2
first
pi
right
force
edge
squared
is
times
3,
pi force,
right?
plus
My
3 pi
far
force
left
squared
edge
times
is
pi
1,
force,
but my
okay.
first
While they're
right
doing
edge
that,
is 3. And then at 5.
we're gonna do
And
this.
then at 7. So
So
I got
what would this be if we squared this right here?
Right, and now I can just figure out what those values are. Well,
I
it turns out
squared
that I now have a graph.
pi squared
Well, that's 3.
over
And then
16
that is 6.
times pi force. Now, a bunch of that is just constants, right?
That's 3. So I'm gonna have.
So isn't that,
6
what's that gonna be?
plus
That's gonna be
12
pi
plus 6.
cubed
So I'm gonna get.
over 64,
Right?
and then an I squared, and what did we say we could do with the constants in the sigma?
Here'd be my right.
Pull them out. So we can take the pi cubed over 64, and only thing left is an I squared from 1 to 4.
But I didn't have to draw them. And I didn't need, I mean, if
Right.
I wanted to get the actual value, then yes, I need the function.
Right.
Maybe I had an equation, maybe I had.
Now, what did we just learn about sigma I squared?
That's how I could get the part in the black. I could get this last part, right? And with the graph, I could.
And what's our n here?
But that, the actual.
4.
right
It was
themselves
n
aren't important
times-
today is this right here.
N
This is
plus
the part that's
1,
important for us, right?
no,
Okay?
oh, was it?
Right,
Yeah,
what
you're
was-
right.
oops.
N plus 2 is 6, all over 6,
10 said
right?
trapezoid sum with 3
So that,
intervals.
right, that came from our I squared, sigma I squared formula. So 6 cancels
So I don't
6.
really want to go any
We got
farther
4
than
times
that.
5 is 20.
Double check.
20 would reduce, well, let's see, the 4 would reduce with the 64,
Okay.
that'd be 16. So wouldn't it be 5 pi cubed over 16?
We want to roll along here. So that's
Will, how you
the
come?
idea of drawing the pictures. Hopefully,
Did I do something
by
wrong?
going through that process, you got the visualization of.
Oh, it was 2n plus 1, wasn't it?
Finding out.
You're
if it's
right,
gonna
you're
be
right,
work.
not
So,
n plus
as
2.
we talked
It was
today
2n plus 1, so what is that, 9?
about,
So this 6 should have been
rerun
9.
sum. So we'll just review this
Right.
quickly. Again,
Isn't
this
it
is what
2n
we
plus
wrote
1?
down the other day. Now remember.
It's n plus 1.
R for Riemann, R for.
Oh, n times n plus 1
R for.
times 2n plus 1.
So a Riemann
Okay.
sum is
All right.
simply a
So
sum
this-
and adding up
So
of.
3 would go into there, okay, so I did
Okay,
that.
Riemann
Okay,
sum,
so-
rectangle
So we
sum.
end up with 15 over 32,
We typically would.
15 pi cubed over 32,
Or midpoints, but as we learned here, they don't.
and that's
have
what you got when you work.
Left to
So when
right.
Will worked it all out
is
here,
just the same
when Will worked
midpoint
out
in
all
the
4 of
sub-
those
right.
rectangles. Now, it's like, let's keep in mind, what is this?
Could be somewhere.
What is this number?
And the widths don't even.
The
have to
area
be-
of
I pointed you to the picture in the. book.
4
Here it is.
right
This is-
rectangles. It's easy to get lost in the weeds
This is a
here.
Riemann
But forget what we were doing.
Okay,
We
this
were
is
doing the
adding up
height
of
times width, height times width, height times width, height times width. We were doing 4 rectangle areas, and it came out to be this number right here.
Okay, and it
Okay.
looks like this
All right.
one's maybe.
Now, the
this
actual
one
area we
maybe
know
a
is
little bit
this.
left of the midpoint, this
Right.
one looks like.
This
maybe
area
a
should
little
be
left of the
bigger.
midpoint. This one's a
Right.
right edge. this
What's
one's
pi
a right
cubed
edge,
divided
this
by
one's
3?
a little
Or
bit
hit control enter on this, give me
definitely right
this.
to the midpoint, okay? And that's
Okay,
fine.
now do pi
That's
cubed
fine.
divided by
We
3
just
and
pick-
hit
We just have
control.
some place in the subinterval that we use to determine the height of the rectangle.
Okay, so the actual area is 10 point something, and here we got 14 something. Well, then that makes sense, that you over approximate these right rectangles be too much, right? So this was 4 right rectangles, but what we did in the blue was easier than what Will did, because he had to type in all 4 of those, right? We were able to just use this little formula here, right? This summation formula, we got the same
The
thing,
width is not the
right?
same.
Now it's gonna come in real handy right now, because guess what we're gonna do next?
Wouldn't have to be, again, 99.
Okay, yes, Will, you will not have to type in 100 rectangles, because we won't have to, right? We can do what we did down here. Now, this is gonna go pretty quick, I'm not gonna draw the whole picture and everything, but what will be different?
You'll see these.
I'm gonna draw myself a little x-axis over here, here's gonna be 0, here's gonna be pi.
So what I was
Remember,
saying
we're doing the
earlier
integral from 0 to pi
is that
of x squared dx, right? So, what are my subdivisions gonna look like, how
the
wide?
part we want to focus on today is the
Pi
right
minus
half
0 over,
of the.
so where's my first right edge gonna be?
Okay, the left, right midpoint, the trapeze.
Pi 100.
So, in
What's my
general,
next one gonna be? If you say pi 50, I'm gonna freak out.
and left rectangles.
2 pi over
starting at the
100,
far
right?
left edge.
3
Now,
pi
remember,
over 100. What's the last
X of
one?
0. We call that
100
X of
pi
0.
over 100, right?
We
Right?
said A,
And that would be, and we could do this with 1,000, we could do it with 10,000,
So
right?
the left input
Right? We're gonna,
started
so
at X of
we're
0.
gonna see a pattern.
Height.
Okay, now,
X of 0 times the width.
so what's my first right edge?
And then we're gonna have f of
My
x
first
one
height?
times delta x, f of x2 times delta x.
F of, right, because we want the y value, we want the y value, so it's gonna be F of pi over 100
Of the far right edge.
times
So the last one's gonna be an f.
pi over 100 plus, let's do the next one,
So when we were going from negative.
F of 2 pi over 100
Edge stopped at 3.
times pi over 100.
2, right? So our last one.
How about that, do one more, F of
Okay, so when you see this, you think height times width.
3
height times
pi
width,
over
height times
100.
width, height times width, you take care.
times pi over 100. Now remember, we got our little x-axis here, I don't need to be the curve up here, but these would be a bunch of right rectangles, we have 100 of them in there.
So again,
Okay, what's the last one?
just to solidify this in your head. So the right will start at.
100 pi over 100. Now, notice that I used right rectangles, and that's what I said before.
Which
Nice
is
thing
the
about
far
right rectangles is they end
First
right here
is
at
one
the
width
right
over
edge.
from the far
Okay,
right
that
edge,
makes it
like we talked
nice.
about earlier,
Okay,
when we were at 1 to
All right.
7, we were doing
So-
1 to 7, we want to do a right.
what was the next step we did then?
Okay, the first one will be 1 width over.
Right, our sigma notation.
Edge, that's x of 1.
So we got I equals 1, 2,
That's, to be honest, that's the one we
100
like the best.
this
We have
time,
our choice.
right?
Just
Because we're gonna add up 100 things, we're gonna add up 100 right rectangles, but we're not technically gonna, we're not really gonna add up all 100. And then what's gonna be in here?
Right, so
F of
the right one is the one we use a lot.
I pi
Midpoints,
over
I'm gonna
100.
write it this way to start here. So midpoints
times
are
pi
a
over
little trickier.
100, there's our height times our width,
They're a
height
little
times our
trickier.
width.
They're harder to
Right, the only thing changing is that top number. Okay, what do we do next?
Notate, what do you call
We
that?
took it out of the F notation. It's just wait, because listen, the function might not be as easy as x squared. It might be sine of x, I mean, we're not gonna run into those, but it could be sine of x plus e to the x, right? And so this would just get way too messy up here. The pattern would be hard to see. So it's easier to just do f of, get the pattern, and then here, do our f of German short order, right? F of German short order means put the German short order in for the x. So we're just gonna take I pi over 100, put in for the x. Now it's easy, it's just x squared. Remember, sine x be sine of
Right now, it's just.
I pi over 100, or whatever, right? We're plugging this into the function. So we're getting sigma,
And then
I
we're trapped
equals
with
1
what we
to
said.
100. It'll be I pi over 100
Because.
squared times the pi over 100. So all I did was take it out of the F notation, plug that into the function for x,
Plus x of 1, but you're.
and now we want to get this constant out of here. So the same thing. This is I squared, pi squared over 100 squared,
Okay, so.
right? I'm just gonna leave it 100 squared for right now.
Yes, we.
And then I got
want to
this pi times
draw 'em. Next
100,
quiz, you're gonna have to draw them.
right? So that means I can take,
Between now and the next.
let me
quiz.
come over to here now. So what do I got? So this, all these constants I can take out, what's that gonna be?
A fair one. Okay.
Pi cubed over 100 cubed,
This idea of pattern,
okay? And then what's in here?
how that plays in, and then of course how that relates to the area.
The I squared.
And
So I got I equals 1 to 100.
Is our goal.
And you're not gonna have to do this from scratch in your homework today, but in the homework, actually, it's in an LH packet, an older LH packet we have, and there's a series of homework problems that are gonna lead you through these different steps we've been doing. You're gonna find some sigmas, then you're gonna do this, blah, 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 and then you're gonna go and you're gonna do the summation formulas like what we're doing here, but they're gonna be, it's gonna be broken up into different parts for each exercise. Okay, so now we get to here. What was sigma I squared again then?
Sigma notations usually
So
do what?
you're gonna get pi cubed over 100 cubed
Add things up, so,
times,
could come in handy.
and now we do our summation formula for sigma I squared, right?
So.
What's your sigma formula for sigma I squared? It's n
Writing.
times n plus 1
Okay, so,
times 2n plus 1 all over
here we go.
6, right?
All right, we've got a few.
So what's that gonna be?
Samples
100 times 101
to start.
times
Okay, so yes, this is
201
sigma notation.
all
Sum
over
of n terms A1, A2, A3,
six.
dot, 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 A3.
Okay, crank that thing into your calculator, see what
Where
you get.
I, so right down here you have.
Give me
this-
the fraction and then
this
give me the
index.
decimal.
A lot of times we use I. The letters traditionally used in the sigma are I, J, and K. Okay, I equals 1 to n. So this number up here is how many you have. If you start at 1, now you don't have to start at 1. You know, you could go 1 to n, you could go
6,
0 to
8,
n
3.
minus 1, you could go 2 to n plus 1, or
so
whatever.
that's-
This bottom one doesn't have to start at 1, makes life a little easier if you start
Say that
at 1,
again.
but it wouldn't have to.
6, 7.
Okay, and a sub I is the ith term of the sum.
I got it.
Okay, so in other
That's
words,
way too
one,
big.
First term and so forth. Notice that the sigma notation does not help you calculate the sum, it just helps you to write
Over how
the
much?
shortcut.
Yeah, are you guys doing the 100 cubed
So
here?
we need two things today.
No, I want this whole thing multiplied
Understand
together.
writing the sums with sigma
I want this
notation.
whole number here.
And then
So,
we're
Emily,
gonna
what'd you
get
have?
a few formulas that will help us actually calculate the sum without having to just add them up.
That's it.
So we have.
Now,
two
give me that as a
separate
decimal.
steps. Okay, so, just to practice that
How
real
much?
quick, so if you had one like this, you have I equals.
How much was
8.
this exactly? Remember, it was pi cubed
Sigma.
over 3. What was pi cubed over 3?
What does that mean that you're trying to accomplish? 3 plus 3.
Now, does it
plus
make
3.
sense that we still
When
are a
I
little
is
too
a 1,
big?
This is 3.
because they're right rectangles. So that, right, and we look at this picture here, the right rectangles are gonna be a little bit too high, but if we have 100 of them,
plus 3, how many
that's
times?
pretty good, right? That's pretty close. Okay, see, and that wasn't bad for writing it, it was pretty quick for doing 100, right? That was pretty quick
What
for
does
doing
this
100.
represent?
Now, we can use our calculator to do the
This is a 1,
Okay,
plus
so
when i's at
how
2,
many would be the
plus
best?
when i's at 3, plus when i's at
In-
4, plus when i's at
So here
5,
we go.
plus when i's at
We're gonna
6.
do n rectangles,
That's gonna be that.
not 4,
Now,
not
right
100,
now, we have no
but we're gonna do n.
other than that above,
So,
we can't-
we're gonna start at 0, we're gonna
So
go to
this
pi,
does represent 21.
and we're gonna divide that out.
Plus 2, plus
into
3.
n subdivisions.
6.
So how
This
wide
would
is
be
each one?
1 plus 4
Pi
plus
over n. Never forget
9
this
plus
formula.
16
The formula
plus
is
5 plus
b minus a
6
over
plus-
n. So b minus a in this
whatever
case
that
would be
is. And
pi
right now,
minus
the only
0
we have a-
over n. So it was pi over 4, then it was pi over 100. Now it's gonna be pi over n. So when you see on your homework, when you see these things written out with n's, that means there's n subdivision, an unknown number of subdivisions. So what's my first right edge gonna be? But you see, you feel how this is the same
But
every
that's what
problem?
this means. So one of
What's
your
this
jobs
first one gonna
today-
be?
So the homework itself.
Pi
is
over
going to
n.
be
What's the next one gonna be?
The
2
homework
pi
is
over n.
just
What's the next
understanding
one?
the notation.
3 pi over n. And what's the last one?
It's gonna be.
N pi over n, right? Which of course simplifies to pi. 1 pi over n, 2 pi over n, 3 pi over n. And what do you suppose we're gonna have inside of our f?
Like we're doing.
In our sigma?
Use the form.
F of I pi over n, right? It's 1 pi over n, 2 pi over n, 3 pi over n. Let's write it out. So what's my first right edge?
Okay.
My first
And then
right
you have
height.
negative, and here you see one that starts different,
F
starts with
of
base at -2. So negative
pi
2
over n
cubed, negative
times my width
-1 cubed, -1.
Pi over
0
n.
cubed, 0. 1
plus
cubed,
F
1. 2
of
cubed, 8. 3 cubed,
2 pi over n
27.
times pi over n.
And
We
of
can
course,
see the
one
pattern.
time I
Let's
can't
go to the
solve
last
it.
one.
So you just-
The last one's gonna be
So,
F of
you just start with the bottom number,
n
go
pi
by
over
1.
n
Always go by 1. Okay, sigma
times
notation.
pi over n.
So you
We
start
can
with
see
the
our
bottom
pattern.
number, you go
Let's
by
write
1.
our sigma. I is gonna go
Okay?
from,
Now, there's a couple of basic
this is so
formulas
cool, I
that
know
we
where
can do
the
with
best thing I
sigmas.
don't have this.
If you have a
I
constant
equals
inside
1,
the sigma,
2,
you can just pull it out
n
front. If you're
F
adding or
of
subtracting
I
two,
pi over n
terms in a formula
times
inside the sigma, you can split that into
pi
segments.
over n.
Okay,
What's the next step?
okay, so those are a couple of properties.
Take it out of F notation. Remember, this is x squared, 0 to pi. There's our F right there. We know the final answer is supposed to be pi cubed
Pi
over
minus 2 is 3.
3, right? That's supposed to be the actual area. So we're gonna take it out of F notation, so we got sigma I equals 1 to n. What do we got?
At IV of 4.
I pi
2 is 18,
Over n squared times pi over n.
and then we can add that up.
So now what's I pi over n squared?
11, 24,
I know I'm writing, you guys are writing furiously. Reminds me of some of the college classes I took, when the professors just be filling the boards all around the room.
65.
Crazy.
Is that one?
Trying to keep up.
Or we can
Okay.
apply these
So what would
formulas.
this be? This would be
Alright,
I
I can
squared
split this into 2 sigmas.
pi squared over n squared times pi over
And I can
n.
pull the 5 out in front of this one.
So when we write this sigma, we're gonna pull out,
Now, these sigmas are both going
what are
from
the
1 to
constants
5.
here?
So this one's gonna be 1 plus 2 plus 3
Pi
plus 4
cubed
plus 5. That's
over
3,
n
6,
cubed.
10, that's 15.
N is a
This
constant
one's
here.
gonna be
N
5
is
times
the number
15,
of
and then
subdivisions.
This one gonna be.
So n is a
1
constant,
pi,
but I is not. So I squared will be in there.
Plus 2 plus 2
So we get
times
I
10. Okay?
1
And so 5 times
to
15
n. Okay, so now we use our summation formula. See how this is all the same?
So 5
What we were doing
times 15
before?
is 75.
Now we got a summation
Minus
formula. Now, we don't have a summation formula. This function would have been sine of I, right? This only
Just
works
show
for
that it's
cubed
just
and
the same.
squared, but it's gonna
Split
prove
that
our point.
part,
So that's
pull
good
it
enough.
right out. Okay.
So what do we got?
Now,
What's sigma
now
I
we're gonna come
squared?
Here in a minute, when we're
N
gonna have the
times
formula for sigma I.
N plus 1
We have sigma I.
times
with
2n
I
plus
going
1
from 1 to
all over
the then we're gonna have a formula for that.
Whoops.
Okay?
Yeah.
Which is gonna become
6.
useful for us.
Now,
So,
this
pretty
time I don't have
basic
anything to
stuff,
plug in for him, do I?
Plug one in, expand
Okay.
these out,
Now,
whatever. Now, where it gets
Here's
difficult
the
is you get
thing.
something like 100, right? You got
When
100
we
of them. Well, this
distribute
one
this
actually
out,
isn't that bad, because this is
Right.
another kind of,
This is gonna be-
special scenario with the sigmas, it's -1 raised to the I.
I don't need to know the whole thing, but what's the highest
Power
power?
1 in for I, what do you get?
N cubed?
Put a 2 in for I. Put a 3 in for I.
Isn't it gonna be 2n cubed?
Oh, it's gonna keep going, isn't it?
Because once you have a 2n times an n times an n, you're gonna have 2n cubed plus a bunch of other stuff.
You have an even number.
N squares, n's, whatever, right? Okay,
But
It's gonna be a big kind of mess.
Now, I know you
Right?
guys did this last year, we were doing sequences and finding
But-
patterns, which is what we're gonna be doing. So if you
now let's think about what we're trying to do.
Two,
How many
4,
rectangles
6,
do we wanna
8,
do
that's
here?
pretty easy, that would be 2i. But what happens if
How
it's
many?
-2, +4,
An
-6,
infinite
positive,
number.
-10?
N is our number of rectangles, so we'll ask the question you asked earlier today. Are we gonna be using limits? Yes, we are. Right now, what we'd like to do with this thing is do what? The limit
where you've used it in the past. We're gonna
As
talk about
n
this.
approaches infinity is what we wanna do.
For example, this one.
Oh, man, I
Okay,
love
this is
coming
probably
together.
stuff you talked
Look at
about.
this.
It's called the arithmetic sequence. Remember
What
that?
happens here as n goes to infinity, especially on this top part?
Okay, in the arithmetic sequence here, you're adding.
When n gets really big,
What is really repeated as
the cube, the high powers dominate. The n squared, the n, the other stuff up here,
Repeated addition.
doesn't matter.
So when you see.
So what do we end up with on top?
What you would think.
We end up with 2n cubed
Repeatedly add
pi
five, so you
cubed
multiply by five,
over
here's what you got. You got 5. So you think, well, this is 5 times
6n
5
cubed.
times 1 is 5, 5 times
Oh
2
my
is 10,
goodness.
5 times 3 is 15.
What's gonna happen?
So wait a minute. That's not 5, 10, 15. That's actually 2 less than 5, 10, 15. So
Pi
okay,
cubed
so this
over-
formula must be 5i minus 2. So that's one way you could come up with that formula if you saw it, right? If you see repeated multiplication, that makes you think of what?
You guys only get to see it once.
That's what
You get to do it twice today and every year for like 20
3
years.
times 3 times 3 is 3.
So that just.
So when you see repeatedly multiplying by a number, that makes you think of
That
exponents,
wasn't
right?
good.
Adding a number makes you think of multiplication, okay? That's what I'm saying.
Look at that.
All right, anyway,
The area,
so just
Under the
your
curve.
idea with,
the area under the
Okay,
curve,
what you might
by
want to put down-
definition, this is gonna be our formal definition, so let's back up here a
before we
minute.
do that.
Well, we did the derivative at one point, we didn't know how to do the
There's a
derivative.
story I gotta
Okay.
tell, famous story.
So we said, but we do know how to do the derivative too.
Never gonna hear this story. It's not
So
good.
let's do 2 points, and how could we get the derivative, how could we estimate it? Very first day class, we said, well, get points really close together, right? Pick 2 points, a lot of you said pick a point on one side and a point on the other side.
Then he was so smart.
Let them get closer and closer together. Okay, that's an approximation, how do we get better? Let them get closer and closer, how can we get exact? Let them get infinitely close, right? Let the 2 points become 1, that's the idea of limit. That was limit as h approaches 0, so that was the definition of derivative.
And told him to
The
add
limit
up
definition of
numbers.
derivative. F of x plus h minus f of x all over h, limit is h approaches 0, we use a limit. Okay, this is its equivalent here for area. We don't, this is why most books actually, a lot of more traditional books start with their integral talk with this, before they get into antiderivatives. Now, I actually like how
So I
our,
proceeded to explain.
the downside to how our book does it is some of this seems anticlimactic, because you're like, I already know how to do
What's
this.
100?
Right, I already know how to do this definition, I already know the answer is pi cubed over 3.
You take 3.
And so you're like, why do we have to go back to this? So, but I still like how we do it, because we can now know that that is the answer. But
How many
but-
pairs did you have?
the bottom line is, we said, okay, we don't know how to do the area under parabola. It's not a geometric shape, but you know what we do know how to do? Rectangles. We can do rectangle areas,
50.
right?
Now we-
So this says, okay, how can you get the area under the curve? Well, do 4 rectangles. Well, that's not very good, so let's do 100 rectangles. Well, that's better, but it's not exact.
So what
How can we
did
get
you
exact?
say?
Well, 1,000 or 10,000. Well, what can we do?
Plus the last
Right?
term.
We can do an infinite number of
Right.
rectangles. That's
And
what we just did. So the
Except
definition of the
multiply
integral,
by-
the definite
multiply
integral
that by the
is
number of terms.
that the definite integral, the area under the curve, can be defined as the limit
Now,
of adding up an
formula
infinite
for
number of
adding up
rectangle areas.
A series or a
If
secret
we can add up an
number.
infinite number of
Okay,
rectangular
that leads
areas,
us to
we've got the area.
these formulas right
And
here.
that is what that leads to. Now, how useful is it?
You might
Not
wanna write
that
down
useful.
your notes.
Fundamental theorem part 2 is way more useful, okay?
On our quiz
And
next week,
approximation
we'll have
techniques like doing
these
50 or 100 rectangles and putting it into a calculator and being able to do
For
this
sure, the
pattern
first three.
is going to be
And if
what
we
we'll do
need
for
the
ones where we
cube
can't
one,
do the
And we'll have that
Right?
one there as well.
This was more theory, okay?
So
Great
these
things
are
we do on Friday
called, so
morning.
in our
So,
homework,
this
and
is
in
more
our,
theory, okay?
um,
But here's
on
what
our
it leads
quiz,
us to, is this right
I
here.
will refer to
The
these
formal
as our
definition of a
summation
definite interval,
formulas.
okay?
We'll refer to these
And
as
so,
our
if
summation
it means
formulas.
adding up an infinite number of rectangle areas, remember, we called that a
Okay,
Riemann
so
sum.
This one's really easy.
A
This is
Riemann
the one
sum
we
is
talked about.
adding
Get
up
3 plus
rectangle
3
areas.
plus 3 plus,
So,
you know, you just take 3 times 4. So if you're adding up
the
a
definite
constant,
integral is
so if you have
basically
sigma
an infinite
constant, so if you have sigma
Riemann
pi,
sum.
and you're going from 1 to 10.
Okay, so the definite integral, the integral from A to B, f of x dx,
Okay, so that's an easy.
is the same as doing the limit as n
The
goes to
second one
infinity,
is the one
sigma
we were just
I
talking
equals 1 to n.
So if I have sigma
And what are you adding
I,
up? You're adding up rectangle areas.
1
F
to
of C sub
100.
I, remember we said that was our sampling
And
point,
we
might
need
be the right edge. We did the right
100
edge today, right? Our sampling
times
point, our C sub
101
I was the right edge. So is x1,
over 2.
x2, and
See
so
how
forth.
that's the same
Okay, but it could be midpoint, could be left, we could have done it with any of
is
it.
the 50,
Rectangle
and
area.
then the 101.
And then delta x is the width.
One more than the
Okay, now, do those look alike a little bit?
So sigma I. So
Do you see what the dx, what happened to the dx?
Sigma I is anti.
You know, we talked about where the dx come from?
We don't. They're not very
When-
good.
When we do, think about this now. When we talk about derivative, we use the notation dy over dx. But where does that come from? It comes from slope,
Okay, so
right?
sigma
What is
has to
slope?
start
Changing
at
y,
one.
we're changing x, right? But if the 2 points
Now,
become
luckily,
1,
we can
what's your
change
delta
the
x
sigma
if you only have 1
start with
point?
1. It's kind of like
0.
sine
What does
wave.
your width of your rectangle become if you have an infinite number of them?
Shifting over one period.
Your width becomes 0 too, right? Now, there is one little technicality on this. Remember I said Riemann sums don't have to have equal widths, they can all be different?
Represent this.
So technically, it's not totally correct to just say your limit, if your rectangles go to infinity. Because you can have one fat rectangle right in the middle that never changes, and all the rest of them
The
get
next
littler
one
and
is
littler.
sigma I squared.
For infinity, you can have an infinite number of rectangles and not get the
Sigma I
exact area, because that
squared.
one fat one doesn't change, right? I mean, that would be it. We're assuming here
Just
that
that.
all the rectangles
So if we were
widths go to 0.
gonna
Right.
wanna add up.
But that's why this dx ends up just kind of hanging out here and not really doing anything, because when we have an infinite number of rectangles, the delta x, the width, kind of goes to 0, right?
Going
And
down
it just, but
then it would be
look at that,
50.
f of x dx, and we can kind of see.
51.
Now all of a sudden, this takes on, or should take on new meaning for you.
Divided by.
When you see the integral of f of x dx, I would hope now you see
That would give
rectangle
us the
areas.
sum.
I would hope you kind of see height
Much
times width,
quicker than
height
having
times
to
width,
add up.
height times width, right? And if this was a rate problem, think of it this way.
Then I
I'm
cube.
gonna get this in under the y. If this was miles per hour, you can now think of the dx as actually having units.
Those are gonna come in here.
Wouldn't the delta x be your hours?
Alright, so
And so
now,
doesn't it make
combine
sense that
all
when
of
you do
these
the integral of
different
miles per hour, you end up getting miles?
to do,
Because it's kind of like you're doing miles per hour times that, right? So
okay,
now all of a
So,
sudden,
you
that
split
dx
this.
takes on a little new meaning.
end
Doesn't
up I
change how we do the
squared
problems at all. But that's where that
minus,
dx
you
comes
pull
from.
the 4
It
out,
comes from that width, that
make that
shrinking
sigma
width.
I.
Okay, now, if I ask you about this on the quiz, I might ask you a question about this. Why is this the area under the curve? Well,
You'll
these
have
4 things
a
are,
bit
I
of
think,
homework.
the important parts of it.
You'll
This
have a
says you're
little
adding up,
homework.
this is the height of a rectangle, this is the width of the rectangle, when you multiply it, that's the area of a rectangle. The sigma adds them up, and the limit tells you you're gonna add up an infinite number, right? I think you should know
So I'll
all
give
the
you something
parts
like
of this,
this. You'll want
and
to
how that gives you that, just like the definitions are made, I want you to know that was slope with each point. Okay, pull out your old LH packet, I'm sorry, Bill's gonna ring you. Your old LH packet, I'm talking, you'll recognize it because it's the one that's got sigmas on the very front page.
Times 2n
It's the
plus
sigma
1.
from before. It's 279.
All over,
Okay, the front page is 279,
right?
and it's got some sigmas on
And
it.
then you can get on your calculator.
Okay.
Now, we're gonna.
Your homework is,
Just crank it out too. That's not that much interest to it, although we.
1 through 8, 9 through 33 odd.
See, and check the order.
1 through
This
8
one has a 4 on
the
the
front
outside.
page,
That's
9
gonna be
through
behind,
33
sigma
odds
and
on
10 plus
LH
1, divided by
page 279.
right?
Now,
And then
it's
plus-
not gonna be as hard as it looks
Times
when
six.
you're going through it, because,
Now
I
we
mean,
get to
it looks kind of confusing, but basically you're gonna expand some sigmas, simple little sigmas, you're gonna write sigma notation, but they're written in nice form, so they're pretty easy. And then the last set of exercises, you're gonna go through that last bit we just did, where you're gonna have a sigma, you're gonna use your summation formulas,
Now, it might be one like
and then you're gonna let n go to infinity, high powers dominate, cancel, kinda like what we did in
plus 25, right, that kind of thing. And then you would
Was that all right?
pull out the 9, pull out the 2, right? Get it down so you had sigma I.
There have been several times I told you over the course of this, when we do these packets, where I said, hey, if you do, we could do this problem, but it'll get easier when we learn some other stuff. Okay?
66,000.
Well, here's what we're gonna focus on now
610.
going forward.
Okay,
That
and that's
integral.
just if you,
Think
so
about
what
this.
that is to understand what that is, that's if you wrote out, so if you
The
put
integral
one
of
in
f
here,
prime,
you'd have
according to
negative
fundamental
1,
theorem
put a
part
2
2,
in here,
is what?
you'd have negative 2 plus, and it would just
F
go
of
on, and it would be this sum
B
of 60
minus
terms. Instead of adding up all
F
60
of A,
of those
right?
terms, we can just
Now
do
think
this.
about that, A and B are the endpoints, and let's say f prime is a rate.
And if this
So
was
f prime is
600
a rate,
terms,
gallons per hour,
right, for sure.
right?
Right, so this.
So F prime is gallons per hour, then what's
that?
F?
Is nice, can be nice.
So isn't this
There's a
gallons
little bit of
win?
work on some stuff, but, all right, so, again, 2 things about sigma.
Gallons
It's a way
win.
to write a sum,
Well, no, just
and
B.
then these formulas are a way to
Gallons
actually.
win, not in this problem, just in general. Gallons,
So it's a little bit of a side
Win.
trip here, because
At
we
the
were
end,
doing rectangle
minus
sums, and we noticed that we were writing them
gallons
out
at the
as a
beginning,
sum.
right?
And
So
so
this is
it's
gallons
right-
at the end minus gallons at the beginning, what's
To
that?
our benefit, to write them maybe in a short.
How much what?
So maybe sigma notation could come in handy.
No, that's not how much you have now, this is how much you have now.
So.
This is gallons at the end.
To,
No.
review our knowledge.
You're getting
about
closer.
sigmas.
Gallons at the
Okay.
end minus
All right.
gallons at the beginning.
That should be enough then of that. All
The
right.
net
So,
change in gallons, net would be where that grows. The net change in gallons,
Connection here between.
right?
one and two.
Now this
All right,
one,
so this
what
would be
were
a
the
pretty
gallons
easy
at the
one. So
beginning?
what I'll do, so there
So
may
it
be
was the
some
same,
part of
so
your
gallons
homework
at
that
the
has
end
some
is the
of
same as the
right
net
sigma
change,
that-
right?
Okay.
We started
So
with
sigma-
0, we ended with 1600, so how much did it change?
Let's start I
1600,
one.
those aren't always the same, right?
What's gonna be in
If
here?
the tank wouldn't have been empty, right, then the
3i.
gallons at the end is not the net change in
10.
gallons.
So the
Right.
first term
So
is 3, the
that
last
just
term
gave
is
us a
30,
really
so
important
this
thing. Now,
would be
this
the
is
last
not
term, this
that
should be
important for
first
right
term.
now,
And again, you
but
see
down the
repeatedly
road. So what we
adding
just
three,
realized is if I do a
multiply by
definite
three, so
integral
and
of
what's
rate of
even easier
change,
about it is we didn't even have to make an adjustment like the one we were talking about earlier, where we had to subtract.
that's
two.
going to give me
So real simple, okay? But sometimes the
Net
pattern isn't so simple. to see,
amount of,
Okay? So on this one, anybody
Change.
got a sigma right up
You got
top of their head?
okay? That's a really important thing right there, and guess what? Doesn't have anything to do with air. That didn't have anything to do with air, right? Nothing to do with air. So the definite integral has now just become a much more powerful tool than just to find some area. Because in the past, you might have been thinking, well, we want to find these odd-shaped areas. They say, what, how often do I need to find odd-shaped areas? Well, this is
I
what
over
we
2,
This is saying that if you do the
Plus-
definite integral of a rate of change,
1/2.
it gives you the net amount of change. Okay?
So when I
in
was 1,
this
that'd
one,
be 1/2 plus
we could have
1/2.
done, so we have a rate of change
Okay.
right here. So
Now,
we could have done the
yeah, I think that
definite
would do it.
integral
And then have
of
to end up what?
300 t to the 1/2 dt.
Check the last
Right.
one, 7 would be 3.5 plus 1/2.
And so let's
Okay.
do
I
that.
think
So
that
the
would be-
antiderivative of this, we found out is
1
200
plus a
t
half,
to
that's
the
1.5,
3/2.
right? So what
Right
you notice
bracket,
is adding
0
a
to 4.
half every time,
So we
right?
put in a 4, we get 1600.
So
We put in a 0, we get 0. The
Which is
net
his
change was 1600. Now, but
But
do you notice what it is? That's how many gallons at the beginning or at the end minus gallons at the beginning. That gave me the net amount of change. Now, since the tank was initially empty, I know that's how many.
Let me
So
show
we gotta
you
understand, is
my
that what
point
it
in
asked?
doing
Did
this
it ask for the net amount of
And
change?
again, not
No,
that
it
we couldn't
asked
do
for
it,
the
but
amount
it took us
at
a
the
little
end,
longer to think
right?
about it.
How many
What
was
if
in
I
there
would've written this
before
this
out?
way?
So that's actually the 1600, right? But this gives us, but we could still figure it from that, okay? So understand, that's 2 different ways to really approach it,
Now how might
okay?
we have written
Now
this?
here's where the real power of this is gonna come in. Go back to that screen I had just a
39
minute
and
ago.
1.
when you have a definite integral, sometimes you can do
Might you not have looked at the top
the
numbers
antiderivative, and sometimes you can't.
and thought
So,
they go up by
We're gonna learn about approximating
one,
definite integrals.
except they don't start
Because
at
we
one, they
can't do the
start at
antiderivative.
2,
So,
so how can I write that?
If you can't, if our rate of
About I
change
plus
is
one
something
up
we
here,
can't do the
and then bottom
antiderivative
row
of,
changes, right? So the
we
bottom
wouldn't be able
rows
to do
just come
this.
back, and then
we'd
go
have
from
to do
1
an
to 7.
approximation. We could still get this
Isn't
answer.
that the same
Could
thing?
you do the red method
Same
without
thing,
being able to do an
right? Same exact
antiderivative?
thing, okay?
Could you do
And
the
now-
red steps without an antiderivative?
So my point in that one is showing you that the way they're written,
No.
sometimes the
No,
numbers,
'cause you wouldn't be
sometimes
able to
the
get
terms
G.
in a sigma.
If you
And
can't
you're
do
gonna see
the
this today
antiderivative
in
of
your
G prime,
homework,
this
are written
method
in a
over
really
here doesn't
strange
work.
way, and you're like, why are they written that
This
way?
would.
Well, they're actually written
Because
that
we
way to
can
help-
find
they're written that
this
way so the
definite
pattern's
interval
easier to see. So
by
in other words,
approximation
a
technique,
2,
thinking of it
and
as
so the
there.
stuff that never changes from term
That
to term
would
is
work.
gonna be
This
in
would.
the
So this has
sigma
great
notation.
power.
And the part that does
Over
change, that's where the I
That
is,
method that we would.
right? The part that does change, which is the
Okay?
top here,
Anytime
that's where
we
the
get
I
the
will
rate of change.
Now, the other thing we
Right,
could
so
have
that's looking ahead a
done
little
on
bit.
this one
On what we're
this
gonna do,
red one
that's
to
a
make it a
really
little
key
easier
concept.
is
All right,
we
back to
noticed
this.
that we add a
Okay, so
half
now
every
we're gonna
time.
dial in and focus
except
on
the first time
approximation.
we
So if
don't.
I have a definite
So
interval, and
what
I
if
wanna
we would've
approximate that
let
area,
this,
what's it look like? So let's go through this one right here. Write this, draw this
Instead
in
of
your
doing
notes.
the
You're gonna be
plus
drawing a lot of
1/2, what if
pictures,
we'd have
and
done
you're gonna be
this?
writing a lot of stuff
What if we
out.
just
So you
said,
gotta
well,
quit
what if
being
we
lazy.
start at
Right?
0?
When I look at
and
homework
only go
tomorrow,
from 0 to 6?
I'm going to,
That would
the
be
only
put in
people that would,
put
I
in
would
a
even
one.
feel remotely,
Or put in a
a
0,
little
we
bit
get our
of,
right? And then we
you know,
put in a 1, we
uh,
get 1.5, we put in a 2.
okay, I can
So
see
we're-
why you
so we
did
don't
your
have this
homework,
other fracture,
you
wouldn't
go
that be the
Miller's
same?
out, Cheers on
Right,
District
wouldn't that give us
5.
1?
And if you're
1.5,
there
2.
tonight,
And then the last term, 6. would
come
give
up
us
and
3
see me,
plus
and I
1.
might give you a break on the homework.
Okay,
But,
so
other than that,
understand, we
I'm gonna be
don't
coming around
have
with
to
this
start
homework tomorrow,
1,
and I'm gonna
and
see
so
a bunch of
sometimes it's
pictures on
easier
your
to write
paper,
if you start at 0 or something like that.
okay?
Which is perfect.
And I'm gonna see a bunch of drawings, a bunch
And
of
we could have
rectangles, a
started at
bunch of
2,
stuff
that's
written out.
probably the one that would have
Okay.
made even the most sense, is you could have said, okay, I'm
So all
going up
these
by a
days,
half,
you know, this is
but I'm
not one of
starting
those days
at
where I
1,
say, hey, do these
so if I just
practice.
go I over 2 and just don't have to add anything.
Or
Right, now
I
you
say,
got-
hey, work a bunch
now you
of
got 2 over
antiderivative
2.
practice
Especially
problems
when
in
you have
gateway
this.
test.
2 over 2, 3
And
over 2,
then
4 over
you
2,
do like
then you say, well, let's let the top go from 2 to 8.
Okay?
Right, if the top's going
All right,
from
so
2
this
to
is number
8,
17. You're gonna do one very much like, one of your homework problems is gonna be very much like this problem right here. So we wanna find this area. Now, we know
So
we
on
can
the
do an
homework, or excuse me, the homework,
antiderivative
but
very
on the
easy.
quiz as well.
We can do f of b minus f of a, right? We're just gonna show on some we know how to do. Matter of fact,
Now
my
let's
slide
get
should
to
show
the,
you.
how this all connects.
Here's
Okay,
the
so
point.
this is the big part.
Here's the point, right?
Okay, so you need to write this
Okay,
down.
if I get on my calculator,
If, as a matter of fact, everybody
And
should
I
stand
do
up here a little bit. We need about
the
a
integral
45-second break. Go ahead and stand up, stretch a little bit. Get the
from
air
0
moving in here a little bit.
to 2
Is it hot in here?
of
I
sine
like the heat on it.
x dx. My calculator does that. Why does it do that? How does it get it? Fundamental theorem part 2. Calculator is smart enough to do the antiderivative of this, and that is an exact answer. Now, if I wanted the approximation, I could go control enter, I could get a decimal, but if that is an exact answer, because it can do the antiderivative. If I change that just ever so slightly, and I go in here and I make that x squared, look what my calculator is. Why? Because it can't do the fundamental theorem part 2.
All right, that's enough.
Because there
Here we
is
go.
no antiderivative of sine of x squared. So the calculator is doing
Research shows
an
too long of a break
approximation
is
technique
counterproductive, so just.
to get it accurate out to a whole bunch of decimals.
True research.
So this is exact out of probably those 12 or 13 decimal places. But that's why it's
Here
giving
we
me
go.
that answer.
We're gonna look at this piece of area right here.
Okay?
Under the
All right.
graph of x squared from 0 to
How
pi.
do we, so how would we do an approximation
Not a
technique
geometric
on this
shape,
one
you
right
can do it with the fundamental theorem, which
on
I've
number
already done.
17
So
in
we
your
got
book,
1/3
it
x
says,
cubed from 0 to pi.
this is on page 355. It says, draw a sketch that illustrates the approximations L4, R4, M4, and T.
Use your pi button, give me a bunch of decimals.
Okay? Then compute each approximation and compare it with the exact value of the interval computed using the fundamental
Yeah,
theorem. Well, we can do the fundamental theorem right now. Fundamental theorem is 1/4 x to the 4th, -2 to 2, Plugging it to 16 times 1/4 is 4.
Alright.
Minus, put in a -2 is also 16.
Seems
4 minus
reasonable.
4 is
Okay, seems reasonable.
0. Does it surprise you that that area is
Yeah,
0?
27,
Yeah,
yeah, 30 something, little bit, divided by 3.
Okay, so we know the exact
So
answer
that's
is
the
0.
area we're
Now, what
looking
it, so we're gonna
Okay, now
compare,
calculate.
So that's the exact thing. Now, they want to do L4, R4, M4,
You'd have to
what?
convert to decimal. Alright.
Well, here's
So
where you
let's
get
say
your-
we were gonna do
So,
4
we're going
right
to
rectangles. Now, we could draw, because 4 right rectangles would be real easy to do. But here's the most
this right
important
here.
part. What I would typically not even draw this whole thing. I would typically just draw the x-axis part of it. So if I'm doing a
And
problem,
I'm going
and
to send
what I think
you-
you're gonna wanna do with these problems is we write out, we wanna write out an R4, we wanna write a sigma notation, which you're gonna see here in a minute.
And I want you to
So
open this one
Then
first.
the most important part of this is just the x-axis part. I really care about the actual
and you're not
rectangles
gonna have
themselves.
to do a whole
Okay.
lot with these.
So, what is the first thing I wanna
you
do? I wanna
have them.
calculate
Did
my
everybody get
delta
it?
x. So that's going to be what?
Okay, you might have to go to the home screen to, find it.
What minus what?
Documents. So the one that
Pi
says
minus
LRAM,
Divided by
RRAM,
4, because we're doing an R4. We're doing 4 right rectangles on this. Now, yeah, it's easy to see that that's gonna be
All right.
this, and they're
So-
gonna be up here. I mean, these would be just
all right, we
really
gotta
easy
move along.
and quick to draw.
So,
Not,
if
you know,
we,
not
if
hard
you
at all.
control
Okay,
and right
but
arrow,
That doesn't
control
matter,
and
don't
right
really
arrow,
need that. But
control
what
and
I
right
do
arrow.
is I say,
Okay,
okay, my
you get to
width
this
is
picture
gonna be
right
pi
here.
4.
So
So
control
that
right
means I
arrow,
need to
control
divide
right arrow,
this
control right
into
arrow.
5 marks. This is
And
gonna be
that's a little
pi
easier
4.
for
I
me on
probably don't even
computer
have to
to do
write
this.
more than the first
But
one.
basically
but
what we
I
have
will.
here
This is
is,
gonna be
see
2
this
pi
L
4s.
lane. Now what
This
that
is gonna
stands
be
for?
3
It stands
pi
for
4s.
left
This would be 4
rectangle
pi 4s. You might be saying,
approximation
why in the world would you
method.
write 2 pi 4s?
Left
Why not
rectangle,
write
you
pi half?
don't worry about
Why?
it.
Because what I just told you a while ago.
These are
Sometimes
four,
you're gonna
these
look
are
at
called
something,
4
right?
left rectangles. Now, we started, that was the day you had to watch my
Pattern
video.
is easier to see if you.
And I
write
went
like
through
this.
and I
If you
drew
don't
some
reduce your
rectangles,
fractions,
and we did
oftentimes
some stuff
it's
with
much
some
easier.
velocities
Pi
and that
fours,
kind of
2
thing.
pi fours, 3
But
pi
if this is the function x squared plus 1, and I wanted to do the area from 1
So,
to 3.
what is my, let's call this F,
Right.
let's call this function.
One way of
F, okay?
approximating that area.
So what is
would
my
be put
first
rectangles under
right
there, 'cause I know how to do
input
that.
is where?
Okay? Now, it's gonna
Pi
be,
fours. So my first height is
right?
going to
It's
be,
not gonna be enough. Right? So what if I
my
had more
first
rectangles?
height is going to be,
Right? Oops. Okay? What if I had more rectangles? That'd be
no,
better.
no, no,
right?
no, no,
But
no,
what
we
we
did
wanna
not
do
do
is just
that.
understand how
We
we
did not
draw
do that.
left
We did not
rectangles.
plug
So
into
there's
the
4
function.
left
My
rectangles here.
first
We got a
right,
distance
my
from
first
1 to 3
midpoint
that's
height
2.
on this one was
So
what?
how wide is each rectangle?
G
Well, each
of
rectangle is gonna be half,
-5.
right?
G
2 divided by
of
4.
-5.
So
Okay,
you're
so
gonna
I'll
have
ask
1 to
again.
1.5.
What is my
1.5
first
to 2,
right
2 to 2.5,
height?
2.5 to 3.
F
So you're gonna
of
get half wide, and then
pi
this one is
4.
how tall.
You don't want to get in
One,
the business
plug
of
that
trying to
into the
plug
function,
that
1 plus 1
into
is
the
2.
function,
So this is
because then
too
that
tall.
just gets messy and
Half
screwed
wide,
up and
2
whatever.
times a half is-
We deal with that later. F notation, G
Right.
notation,
This one, you
function
plug a
notation is how I
1.5 in,
understood
that's
the
gonna
first
get
time.
into decimal.
So my first right
So
height is an F of pi 4.
So
What's my
anyway,
width?
that number is gonna be too small.
Pi
What would a
4
right rectangle?
plus, right? Height times width, height times width, height
right
times width, height
rectangle
times width. Okay,
approximation.
what's my next
So
one?
look what we did here, we still divided it up
F
into
of
4 subdivisions.
2 pi 4.
But
Don't
this
you dare
time,
write pi half.
Our
F of
right
2 pi
edge,
4s
is
times
we're gonna call these, a lot
pi
of people like
4
terminology.
plus
This is called a sub-interval. Our interval
F
is
of
1
3
to
pi
3.
4s
We
times
divide it up into 4
pi 4s
sub-intervals,
plus,
okay? And so here, the right
I have to go
rectangle,
one more because we need
take
4
the
of
first
them, and the
sub-interval,
right edge
we
should
go
be
to the
your
right
last
edge
right
of that
endpoint.
sub-interval, and we go up to the
Right, your
function,
last
and we let
right
that be our
rectangle
rectangle.
height should be at the
So
far
a
right edge.
rectangle width is down here.
4 pi 4s.
And a rectangle height is our
Now,
y.
the goal is,
Right?
we want to
So
take this one
rectangle
step
height is our
farther
y back,
than
as
what
you
we've
keep
done
going.
in the past,
So I
which is
just
down
want
1
1 and a
right
half
into
into
sigma
the
notation.
So notice,
So,
that area is
There's a
gonna be
little
too
room,
big,
we've got a
right?
couple
That's
things to
too
do here
much.
yet.
That's
So
gonna be
this
what we
is
call
going to go
overapproximation.
from something to
Whereas
something,
the other
and
page
let's
is an
look at our
Right.
terms,
Okay,
okay?
so
Now
that's
look at
left
that term.
rectangles, right rectangles.
And then look at that
you've
term.
got midpoint
Then look at that
rectangles.
term.
Now,
And then look
midpoint
at that term. The
rectangles, you
vast
notice, might be a
majority
little
of that
bad. That's kind
never
of a compromise
changes.
between
The
two.
only thing that
So the
changes is
midpoint
what?
rectangles, what we do, again, we have 4
The
sub-intervals.
top of the
We take the
inside.
halfway
It
point,
goes
so
1
between
pi,
1 and
2
1.5,
pi, 3
that'd be
pi, 4
1.25.
pi. So what do you
Now we
suppose is
plug
gonna go on the inside of
1.25
the
into
sigma?
the function, and that gives us our rectangle height.
F of,
So our width is still
what's gonna be on
0.5,
top?
and our height is whatever that function value is.
Not just
Width.
I.
Now that seems to give us a little over and
1
under,
pi,
and so
2
that's
pi,
gonna be a
3
better
pi, 4 pi.
approximation, right? That's gonna be a better approximation.
I pi.
Okay, and I think that's the last page. Okay, so just
pi
to get that
over
picture right,
4
you guys are
times
drawing these pictures.
pi over 4.
Okay.
Look, every single one of those terms has a pi over 4 outside of it.
Okay.
Every single one of those terms has an F.
So-
Every single one of those terms has a parenthesis.
Another
Every single one of
picture
those
to
terms
show.
has a fraction
Okay,
mark.
so here's an
Every
area,
single one of those
or
terms has
maybe
a
B.
4 on the bottom. Every single
Okay.
one of those terms has a pi on top. The only thing that changes is the 1 in front of the pi, then a 2, then a 3, then a 4. That's going to be the I. The part
Okay,
that
there's
changes
4
is
left
where the I
rectangles.
is going to come in. So this is f of I
Left
pi
rectangles.
over 4 times pi over 4. Isn't that the pattern we see?
Divide it
right
up
there?
into 4
And
subintervals.
that's how we write a sigma. We see the
Go to
pattern.
the left edge of each
That's why I
subinterval,
was so
up to the
picky
curve
about
or
you
down to
writing
the
this
curve.
out.
If it's down here, right, might be negative.
Writing that out, because if you write it
And
out
then you go
properly,
straight across,
sigma
draw a
is
rectangle.
easy to write.
Up to the
And
curve.
the eyes are gonna go from
Draw
what to what?
up to the curve.
1 to 4.
Okay.
Now,
If you want
let's
to do
get
right
out of
rectangles,
F
they
notation.
would be in the blue.
Now, let's plug in.
There's
F of
4
I pi
blue
over 4
right
means what?
rectangles.
F of
Make
2
sense?
means do what?
Okay? Seems
F
like
of
it should
2
be real
means
easy,
what?
but sometimes it's a little confusing.
Plug a 2 into the
Midpoint.
function. F of 3 means plug a 3
Just
into the
do
function.
our
F of
same,
German
divide it
shorthand
up into our
plug
4
a German
subintervals,
shorthand
and then we
into
take
the
the
function,
middle of
right?
each of the
F
subintervals
of I
and we
pi
go up
over
to the
4
curve.
means
That-
what? Plug an I
And
pi
here's the
into the
actual
function.
area
So
right here.
this is
So
going to
notice
be
this is better,
sigma
this is closer.
I equals
The
1
right
to
rectangle
4.
was too much.
And this is going to
All
be
of this
I
over
pi
approximation
over
here
4
kind of offset this
squared.
under
Now that's simple
approximation here.
because it was such a
My
simple
left
function.
rectangles were a
This
little
might
bit
have
too
been x
small.
squared plus
Had a little
3x
over
minus
here, but had a
7.
lot of under
And then we'd have went
approximation
I
here, so
pi
they're
over
too
4
small.
squared
Midpoint's better.
minus 3 times
Okay.
I pi over 4.
And then one of the things we talked about in that video you watched that very first day we did chapter 5 is
in
traps.
wherever
So
the
the
X
other thing
was.
you can do is
Well,
trap.
we just have that one
You
edge.
go to the
right
left
there.
edge, you can go to the right edge. and
So
you
if the
can connect
function is
them,
more
and that would
complicated,
make
it's
the
always
triangle.
way better to write
And
this
that's
in
kind of like a
notation
midpoint. It's kind of like a,
because the pattern
it's kind of like a
write a sigma,
compromise.
and
right?
then we can plug it in.
So it takes care of a little bit of the over, a little bit of the under. That's a little better. Look, and then of
Alright.
course, but
Now-
here's the real secret.
Yes, it's
Real
only 4
secret
right
is,
rectangles.
if we do
I
enough
get it.
of them.
We could have right here,
It
on
doesn't
your
really matter.
calculators, you guys could have said, okay, pi 4 squared times pi 4s, plus 2 pi 4 squared times pi 4s, plus 3 pi 4 squared times pi 4s, plus 4 pi 4 squared times
Okay.
pi 4s. Boom, 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 equals, got your answer, right? Well, what if there's 100? Oh, well, we're gonna do that in a minute.
I mean,
right?
you know what I
So
mean?
if there's
If you get
100,
enough left rectangles,
That would
you get a
be
pretty
off.
good approximation.
right?
Right?
So let's
even
do
though
this.
midpoint's
You know what
better.
we could do
Yeah,
here?
if
We
you
could
wanted to
square
say,
this.
hey, if you do 100
What would this
rectangles,
be? This would be
what
I
would be better?
squared
Well,
pi
800
squared over
or 100
16.
midpoint rectangles would be better than
Now,
100 left.
isn't pi squared
Right.
over 16
But-
constant?
That just meant that
And
all
pi
that
over 4
matters is
constant?
how
What can
many
you do when
decimal
you
places
multiply
you
by a
want to be,
constant
right?
inside of a
You're going to
sigma?
do 1,000.
Can't you pull
You're
it
going to do
out?
1,000,000
So can't we pull out the pi
Doesn't
4s?
matter. You can do left,
Can't
you
we
can
pull
do
out
right,
the
you
pi
can do
squared
midpoint. They're all
16
gonna
and be
eventually
left
they would
with what
get really,
inside?
really close to the actual area, right? Now, who in the world would want to sit here and calculate by hand?
When we just
right?
left with I squared
Dude,
inside?
Our rule's going to kind of
We
be
go ahead and square this, and
If
that
it's
becomes I squared pi squared over 16.
Under
We can
10.
take the pi squared over 16 and the
We're
pi
gonna
over
do it
4,
by
we
hand.
pull those out.
right?
And we just have I
Single
squared.
digit
Well, wait, we learned the
subdivisions,
formula
we're
for
going to
that.
calculate it by hand.
We learned the
If it's
formula
more
for
than
that,
that,
so
we're going to
isn't
have
this
a
going to be
program
pi
where we
over
have
4
anything on our
times
calculator
pi over 16
type into.
times, and then what's
We're gonna
sigma
write
I
it out.
squared? Isn't that n
Okay, so
times
those
n
are
plus
left
1
and
divided by
right
2?
rectangle.
Isn't it, right?
Okay, so
No, that was, oh, yeah, it is, you're right. It's n plus 1, 2n plus 1 over 6. That's what it is, right. Okay, so this sigma I squared is going to be n, which is 4, times n plus
So,
1, which is
let's
5.
go to, well,
times 2n plus
let's-
1, which
so let's
is-
go back to your picture. So let's do blue. Let's start with blue. So it says
2n
to do
plus
L4. That's how we're going to
Because our n is
abbreviate
4 here, right?
4
Whatever
left
this top
rectangles.
number is,
We're
that's
going to
the
call
n.
that L4.
So that'd be 9 divided by
L4 is going to be 4 left rectangles.
6? Okay.
And we're
So we
supposed to do
work that out.
R4, M4, and
So,
T4. We're supposed to write
Forget the
that.
pi squares, we'll do that in a minute here. So 4
And it
times
says
5
draw a
times
sketch.
9,
It says draw a sketch,
do that.
and then compute the
Divide by-
approximation and compare it to the exact value.
Divide
So,
by the 4
I
times
need
16
4 left
times 6.
rectangles. So let's go in here and draw. First of all, we got to figure out how wide are they going to be. 1 wide. And why is that? Because our total width is 4, and we're going to divide it up by 4.
15
Now,
over 32,
In general,
pi squared.
that's called this right here. And we usually call that delta x for change
Oh,
in
yeah,
x.
this is supposed to be pi
The
squared.
width of our
Pi cubed.
rectangles
So
is
15
going to
pi
be called
cubed over
delta x.
32.
Change in x.
15
Same
pi
time,
cubed over
Delta
32.
y over delta x, right? It's
And what is that
right,
as a decimal?
Basically.
Okay, so we're gonna divide that into 4 subintervals. So that's gonna be 1, 2,
How much?
3, 4. Now notice it took 5 blue marks to divide
Is it
that into 4
surprising to us
subintervals.
that was
make
quite a
sense?
bit bigger than
You start here,
10.335?
1, 2, 3, 4
Is that
subintervals.
surprising?
5 marks to do 4 subintervals. It's always
Is
one
it
more.
surprising that
That's
my
gonna
4
give you
right
one more
rectangles
definition.
were quite a bit bigger than the actual blue area?
So 5
Not
marks
surprising at all.
will give us these 4
Every
subintervals,
one of
and
them
they're
is
gonna
an
be 1 mark.
approximation.
So
not
my
surprised
first
that that came
left
out.
rectangle, we're gonna go
Okay.
down
Well,
here
about
on the
100
left
of them
edge
would
to
be better.
here.
Wouldn't there
We're
be
gonna
less
go over
error
1,
for 100 of them?
and then we're
Boy,
gonna
100
draw
of
them
them that'd be
there,
awful. No.
and that is going
100
to
of them
be
is,
our first
because of
left
what we just
rectangle.
did, 100 of them is no worse than doing 4 of them. Let's do it. Okay, so what do I got over here? So I got 0
Right?
to pi still. I want to do 100 right
Now,
rectangles.
for the sake of time, we're only gonna draw one of
I
them.
wanna do
but we're gonna
100
write
right
out 4 of
rectangles.
them.
So-
On your homework,
What do I got to do first?
on your homework, when you do one of your problems, gonna be similar to this one. You'll have 4
Delta
pictures of, you'll have 4 drawings of
My
this
delta
graph.
x is going to be
Okay? If you wanna get the homework points, you're gonna have 4 drawings of this graph.
pi minus 0
You'll have 4 left
over.
rectangles on one of the pictures, you'll have 4 right
100.
rectangles on one of the pictures, you'll have 4 midpoint
So the
rectangles.
width is
on
gonna
one
be
picture.
pi 100.
Okay?
Right?
Alright, so
Pi
now,
100. So
let's
now I
keep
come
going.
over here to my x-axis. I
Next
don't
one.
care about the graph.
so we go to the next subinterval, we
Right.
go to the left edge, because we're doing
First
left
right edge,
rectangle.
pi 100.
And we're gonna
What's my next
go
one?
to the curve, and then
2
across,
pi 100. What's my
and
next
there's
one?
going to be,
3 pi
our second
100.
left
Dot, dot, dot. I'm not going to be able to fit all those in. What's this last one?
then we're gonna go to the next subdivision.
100 pi 100.
Where's the left edge on
What's
this
the one right before it?
What's the height?
99 pi 100.
So-
right? That's enough.
Sometimes we get
did that. I
no
see the
rectangle
pattern.
at all, I usually kind of
Right?
draw it in
There's
kind
gonna
of
be all
thick
my
just
right
to
edge.
show,
I'll
hey,
have
there
right
is a
in,
rectangle here, it just has a 0 height. So it's gonna have a 0 area.
Okay? All right, let's
Okay,
start
and
right
then
down
the
that
last
side.
left rectangle
Okay, so
is
what's
gonna
my
be
first
there
right edge?
to there,
Pi 100.
right?
So first, what's my first right
Now,
height?
let's draw that out.
My first rectangle height.
I'm sorry, write that out.
F of
Now, here's how
Pi
you're going
100.
to do this. I
times
want
the
to
width.
see in math notation,
Pi 100s.
the area
What's
of
my
each
next
of those 4
height?
rectangles. Okay?
F
So
of
the first rectangle has
2
what for
pi
its height?
100s. Times
Now, how do you get -8?
the width
By
Pi
putting a
100s
-2
plus
back
dot, dot, dot,
into,
dot,
this is F of
What's
X
the
down
last?
here, by the way.
right
That's
height.
F of X. So F of
100 pi 100s.
-2 is what I want you to write. I want you to write it in F
Times
notation. Now, I know it
pi
kind of
100.
sounds like I'm
My last
you
right
know,
edge would be
making a
at the
big deal
far
about
right edge,
writing
which
this
is
out,
a
showing
pi,
you
which
worked
is
out being
100
lazy, and I
pi
am.
100s. And so
Because,
now what I
but
need to
there's
do
a
is
reason.
write that
I
as a
just busy.
sigma.
right,
I is going to go from
where we're headed with this is seeing
1 to
patterns.
100.
We want to see patterns. And the more you write it out, the easier the pattern
Look at each
looks.
one of those terms.
Now, times, what's the width on this?
What never
What's the width?
changes, what
One.
does change.
Now, it might seem kind of silly to
every
write the
term
1,
has an F.
but I want to write it.
Every
Because
term
when
has
you look at
parentheses,
this,
every term
again,
has a fraction
gonna
mark
go
with
to the
100
pattern
over it,
we're
every
talking
fraction,
about. I
every
want you
term
to
has
see
a pi,
height
every
times
term
width.
has a pi
Because I
100
want you to
over
see
here.
this and think of
The only
area.
thing that changes
I want
is
you
the
to think
number
of
in
this
front
as
of
that
the
blue
pi
area.
goes 1 and 2, then
So I want you to
3,
be thinking, rectangle
dot,
height,
dot,
that's
dot.
the F, that's the Y value,
100. So
and
what do I
then
got
rectangle
inside?
width. Height times width, height times width,
I
height times
pi.
width is there.
1
Okay,
pi,
plus,
2 pi,
what's the
3
next?
pi, 4 pi.
Height.
Now, it's not an accident that we're using
F of
right
-1
rectangles here because those start
times
at
1
1. Those remember
plus
started at
F
x of
of
1, ended at x of n. They're
0
nicer
times
notationally.
1
So we
plus
chose right
F
ones
of
to do here, but I'm going to show you
1
what it changes.
times
there.
1. Notice we don't get all the
But
way
there
to the 2.
that
do
is.
we?
Okay, now what
With our
was
left
the next
rectangle,
step?
we did not have anything at the 2, right?
We
We
do
started
like what
at
we
the
do in the
left
last
end.
problem,
We don't
next.
get all the way there. Well, that's because there's 5 of these
We took
marks,
it out of
like I
that
said earlier.
notation
There's
by
5 of these
plugging it
marks
into
to
the
divide it
function.
into
So now we
4
take the
subintervals.
I pi over
We're only gonna
100,
use
plug it
4.
into the function.
So we don't
So now we
use
got
the one
I
we tried.
equals 1 to 100.
Okay, now let's do right.
Instead of
Now
f of I
I'm
pi
gonna
over
do this
100, we got I
again
pi over 100
so we can see it, and then I'm not gonna do that.
squared,
Um,
because we're plugging it into our function now.
Well, no, I will too. I tell you what, let's don't do it.
Okay?
Let's do it.
Now let's rewrite that. Let's simplify that a little bit. This would be
Okay,
I
I'm not gonna
squared,
draw the right
I squared
rectangles in
over
there.
100
Okay, but I
squared,
will talk about them. The
right?
right rectangle, so here's your
Now
first
can I
subinterval.
pull
Where
out
would we
some
go
of
to
that?
draw our first height?
I can pull out the pi
We
squared
would go
over 100
here to the
squared.
right edge, and we would go to the curve, and
pull out
then we
the
would
pi
draw
over
backwards
100.
like this. Now,
Is that
this
right?
is why you're not gonna
And
get
what
to
am I
draw
left with
yours
inside?
all on the same picture, because it gets too messy, you can't see it.
Just I
So
squared,
you're gonna have 4 separate pictures here,
right?
okay?
Now, I
That's how you
can
go to
only have
right rectangle,
formulas
you
for
draw
I and
backwards.
I
So you go to the
squared.
first
I cubed,
subinterval,
so we can only do
you go
simple
to the
polynomials.
right edge, you go to the
Just like what
curve,
we did,
and then you
the
draw backwards.
definition of the derivative,
For that.
we did x cubed and saw that it was
Okay.
2x squared.
All right,
We
so
did
the
x
right-
squared and saw that
so
it
what's
was
my
2x,
first
right?
height
That didn't work for sin x.
of my
that didn't
first
work
right
for
rectangle?
But we at least could see it nicely.
F of
working for those,
negative
and then
1
we could apply it
times
to
width
the
of
rest
1,
of them, okay, and that's what
and then
we did
F
here.
of
So what is this sigma equal to? So this is
0, because my
pi
next
cubed
right rectangle is
over
gonna be here
100
at
cubed.
0. And then we go that way.
Sigma I squared
Okay.
is what? 100
Then my next one's gonna be there. Here I
Times
said I'm gonna draw, it's
101
gonna get messy. There's my next
times-
right rectangle. My next right rectangle, my last right rectangle will go up there.
201
Come down.
all over,
And my right rectangle will be this
6.
black one here.
okay?
Okay, so it's F
Well,
of
this
0
100
times
will
1
cancel one of
plus
those
F of
anyway. We can at least do that. Okay, so now divide.
1
multiply
times
that out on
1
our
plus-
calculators here.
F of 2. So here I actually use the 2, because my last rectangle goes up here at 2 to that y value, so that's F of 2 times my width of 1.
Maybe.
So this time I didn't use my left hand when I started with my right, did my right rectangle. Okay, M4.
My calculator's taking forever.
Now M4, where do I go, where am I gonna go to do this one?
Divided by 100 squared.
Right in here at -1.5, right? And I guess I could do that, I don't know, I don't wanna use green, because that would be up for traps. So that would be, I would go to the curve, which would be about here, and then I would draw
Wow, that's
both
pretty good.
directions. And then that would be my
10.491. What was the
midpoint
actual
rectangle.
area?
So we go to our subinterval, we go
10.35.
halfway to
So
the
a little
midpoint,
bit over,
and then we go to
not
the curve.
surprising.
You always go to the
Every
curve
rectangle will be a little
for
bit
your
over
rectangle
100.
height. Always go to the curve for your rectangle height.
10.491.
So there's our
That's not
rectangle
bad.
height,
That
so we
wasn't
draw
too
both directions for
hard.
our
I mean,
rectangle top.
computationally, that was
And then
not
there
hard.
is our midpoint rectangle.
Right?
So that would
was
be F
not
of
hard.
what?
For doing 100 rectangles.
Negative
was not hard.
1.5
Okay,
Times,
it only
what's our
worked
width?
Because we had a nice function like x squared.
Still
which allowed
1,
us to
right?
do
The
this
width, the
simple
subinterval
height.
width is still 1, that doesn't
Okay,
change.
But here's where it
Plus F of, what's our next
Yeah,
midpoint gonna be?
So, four
Negative
rectangles
0.5
was not great, pretty easy to
times
write.
1
And now we just realized,
plus
well, 100
F of-
rectangles was really not any harder to write. When you
positive
look at what we
0.5
wrote there,
times
you look at what we
1
wrote there.
plus
pretty
F
simple.
of
Well, what would be a better number of rectangles?
1.5 times 1, right?
Huh?
Now, on our next
Would be
quiz,
better than
I'm probably
10,000.
gonna let you use calculators on our next
Million
quiz.
would be better than
Right,
million.
so then you can type these
Infinite
numbers
number of
into the
rectangles
function.
would be better.
Now remember, the
An
function is
infinite number
this,
of
not
rectangles
this, this
gives
is
us
the
the exact
anti-area.
answer.
We always plug it back in
Think
here,
about
the
it.
whole point
If
of
you
using
keep
this,
getting a
because
better
it's
and
the
better
area under little
approximation,
f,
the
the
more
whole point of
rectangles
using
you do,
approximations is
doesn't make
because
sense
when you
eventually.
can't do an anti-derivative, right? So we're not,
If you
one
could
time
get to
we
an
do our
infinite number of
anti-derivative,
rectangles,
we're doing
that would
fundamental
give
theorem part
the
2.
exact
Right,
area
then we're not
under the
doing these
curve.
rectangles, so we're always plugging it back into this
So let's do
function
it.
that's in here.
Now, how do we do an infinite? We can't do
Okay, now,
R
last one is
infinity. We're gonna do R n,
T4.
and then we're gonna let n go.
Or
to infinity.
trapezoid.
So we're gonna do n rectangles. Now, what
Now,
has
what's the
changed?
formula for a
What did anything?
trapezoid?
We
It's
still have our
1/2.
x-axis. It's gonna go from 0 to pi. Right?
The two
Got a
parallel
graph up there. We're
bases,
gonna do
right? Well, what would be our
rectangles.
parallel
That's our
bases?
second
Well, it would be
calculator.
this side,
My width.
and it would
Delta
be
x is going to be
this side, right?
pi
And then
minus
we would
0
connect
over
those.
n.
That's how you make a trapezoid,
Pi over n.
right?
So
Yeah,
the
we've done that
first
already.
right
We've done
edge is
that.
gonna be pi over n.
There's our
What's the next
trapezoid.
edge?
Okay, so what is it? It's f
2
of
pi over n. I mean, think about it. What's pi over n plus pi
negative
over n?
2
You add the
plus-
tops. When you have a common denominator, you add the tops. Keep the denominator the same. Pi over n plus
F of
pi over n is
negative
2
1.
pi over n. Plus pi over n is 3 pi over n. So the next one's going to
Times,
be 3 pi
what's
over
our
n. What's
width?
this last one going to be?
still 1.
N pi over
Plus,
n.
what's the next trapezoid? 1
N
half
pi over n. What's the one before it going to be? N
f
minus
of
1
negative 1
times pi over n.
plus
Right?
f
N
of
minus 1 quantity.
0,
times pi
and then all
over n.
times
It doesn't
1. Now
matter.
look at the
Okay,
picture
what's
on
my
it.
first right edge going to be?
Look at the picture on it. Now it's getting really messy, and that's why you're going to do 4
My
separate
first
pictures.
height is going to be
But here's
f
f
of
of 0.
pi over n.
And here's f of negative
Times
1.
the
And when I
width
connect it,
pi
what do
over
I
n.
get?
My next height's going to be 2
Actually, I
pi
don't get a
over n.
trapezoid, I get a triangle. And
Times
sometimes that happens.
pi over
Matter of
n.
fact, sometimes if your
Plus
curve
da, da, da,
crosses,
My
the
last one's gonna
x-axis,
be
you might have
pi
this
over
edge
n.
here and this edge here, but when you go to do your
Times pi over n,
trapezoid, it actually ends up being
It's
two
easy.
triangles, right?
It's
So
easy to
sometimes
write.
a trapezoid is a
We
trapezoid.
do the same thing in all
sometimes
of those
it's a triangle,
cases. We first
sometimes it's
determine the
two
width.
triangles, right? Because one
Depending
edge
on how
is
many
up here, the
rectangles
other
we
edge is
have,
down
so
here,
it's
when
a
you
p
connect
minus
the
a
actual
of
tap,
total
but we
width
still
divided
call
by
it
half the
trapezoid.
subdivision.
It's still gonna be this form.
When we see an n in there, we
All right,
can't get freaked
plus
out by it.
One
Just take
half
an n.
f
The
of,
width
what's our
is
next
pi over
one?
n, so if we're starting at
Notice how you
zero.
reuse, right?
Now,
The
this
right
would be
edge
more
of this
difficult
first
if we didn't
trapezoid
start
is the
zero.
left
This
edge
integral
of your
went
next
from one to
trapezoid,
pi.
right? You
What would
reuse
be my
them,
first right
except
hand
for
point?
the ones at the
Your
end.
left edge
So
is
f of 0
1.
plus f of
You
1
move over pi over n, what would you call
times
that?
1. And then plus
1 plus pi
1
over n.
half, we got one more
And then
trapezoid,
1
f
plus
of
2 pi
1
over n. And then 1 plus
plus
3
f
pi
of
over n.
2
Whatever your
all
left edge
times
is,
1.
you just
And you
move over
notice
one width,
that
that's
you
your first
use
right edge.
all of those edges,
your left
those 5
edge
edges,
of the
when you're
whole
doing a
interval is here,
trapezoid. Is you use the
and you
left
move over
one,
one width,
it's
that's
the
your
left
first
edge
right
of your
edge,
first
which in this case,
trapezoid, and
0
then 2
plus
is the
pi
right
over
edge
n.
of your
Okay,
last
now our
one.
sigma.
You only use those ones, the ones between using it. Those are all
This
the
is
little
the
things we're
sigma's
gonna be
gonna go
picking
from
up
1
on as
to-
we go along in seeing the
And
pattern.
this is gonna be
Okay?
f of.
So once you have that written out, now you can easily just calculate those
I
numbers.
pi
Let's just do the very first one. You're supposed to
over
actually
n
evaluate, so let's do the very
times
first one.
pi over
So
n,
this was
isn't it?
negative 8. And
Isn't
then
that gonna be
negative
it?
1 cubed is negative 1.
Okay, just tell me to slow down.
And then
if
0
I-
cubed is
if you need
0. And then
Carry
1
it a little
cubed
bit.
is 1.
to. I
So
know where this is
negative 8
going.
plus negative
Right?
1
F
plus
of
0
I
plus
pi
1
over n.
is what? Negative
That's
8?
the pattern, 1 pi over n, 2
That's
pi over n,
clearly
3 pi over n.
not
I pi over
0,
n.
right? It's
Okay,
a
now what
horrible
we do is the next
approximation.
step.
Well, 4 left rectangles usually
Take
is
it out
not a
of
very good approximation,
Sigma,
right? I
or
mean, look at all this
not
blue
sigma,
area we
application.
got here.
so instead
These
of
balance each
f
other
of I
out.
pi over n, we're
But
gonna
then we
take I
got
pi
all
over n
this
and plug
area up
in
here
for
that we
x.
didn't account for.
So we're gonna
So
get I
we
pi
got all this blue
over n
area that's way
squared.
too much negative.
And
Times
so,
pi
yeah, we
over
don't
n.
get a great approximation. But that's not what we're
Now
building
what?
for. We know a great
Isn't n a
approximation would
constant?
be 100 left rectangles.
Isn't it a
1,000
constant, right? It's the
rectangles.
number of
Right, well,
rectangles.
even I'm
Now,
too
yes,
lazy
we're
to
gonna let that
write
go
out
to
1,000.
infinity, so you might say it's changing,
Right.
but it's, every
Okay,
term is
so
the same
we're gonna
number.
come up with a
Right,
pattern,
it's a
and we're
million
gonna come
or
up with some
10,000,
formulas.
every
We're
term
gonna
it's the
come up
same
with a
number,
way
so it's a
we can do
constant.
this.
So,
We're gonna show
what can
how
I
to
pull out of
calculate
this?
it.
I can pull out
What we talked about earlier. Okay, but this is
pi squared over
an
n squared,
approximation
and then a pi over n, so
and
we'll,
how
well,
we're
I'll just
doing
write it,
that.
because that's what
So,
we'll see.
if it's
Pi
under
squared
10,
over
if
n
it says
squared,
do an
and also
L8
pull out the pi over
or
n, so it's gonna be
R5 or
pi
whatever,
over n
we're
cubed
writing
over
it out.
n.
We're writing it out.
And then what am I left with in here?
We won't
Pi
always
squared,
draw them,
right?
but
This
if
is
drawing them helps
exactly
you write
like
it
what
out,
we did
that's
with the other
fine.
ones.
But
Okay,
we're gonna
now,
need to be able
what
to
do we
draw.
got? We got pi
On our next
cubed
quiz, you're
over
gonna
n
draw
cubed.
some, you're definitely gonna write
And
out.
now what's sigma I squared?
And you'll make you both on the same problem. Okay?
N times n plus 1 times
Let's go
2n plus
to that
1.
other, real quick, to that
over
other
6.
document I sent you.
Hold on a
You
second
don't have
here.
to pull it up right
Now.
now. You can pull it up later. This
Okay,
is called,
now,
notice
we
it's
can boil
called
this all out.
Riemann. That's how you pronounce that.
Okay.
Riemann.
but I'm going to
a
do this.
Riemann
This
sum.
is
That's
pi
named after a
cubed. The
German.
top here is n cubed
Riemann.
plus
Okay?
some other
now,
stuff.
This is very similar to that other one. The difference
Okay.
here is you can
Would
change
you agree?
how many
No,
you
no,
have.
not n cubed.
Okay, like if I want to do 4 left rectangles,
My
fine.
bad.
Or I can grab this slider and I can do more.
It's actually going to be what?
Right? So it's kind of cool.
2n
So I can grab this slider and I
right?
can do more.
Because I got an n
And
times
if
an
I'd
n
rather
times a
do,
2n. This is going to be 2n
midpoint,
cubed
I can just grab
plus some
this
other
guy.
stuff. And
and
then
I
there's
go
going to
over
be
here
an
and I
n
do
cubed and a 6.
Okay, and I
on
can
the
grab
bottom.
that and I
Would you
can
agree
come
with
over
that?
here and do right.
So I'm going to have pi
And I
cubed,
come
I'm going to
over
have
here
2n
and I do
cubed plus
travel.
some other stuff. And I got
Okay.
n cubed and I
And I
got
can
6.
slide
Now
this
why
and
in the
see
world
how
would I
many
do
you
that? Why would I just do the top as 2n cubed and then not
Okay.
care about the other
All right.
stuff?
So that's basically, that's
Because
it.
we're going to let n
for
do
that.
what?
But it's just a way for you to visualize
Go to infinity,
what
and when
these
n goes to
different things
infinity,
look like. Okay, so it's just a
the
tool
high
for
powers
you to
dominate,
use.
and the n squareds and those aren't going to matter.
Okay,
Well, we're, right now,
rectangle.
let's put it red,
All right. So you got those.
right
two,
now, we're going to
those
say,
two
okay,
things.
let's let n go to infinity.
So now in our
When we
notes,
let
we're
n
going to
go to
write down
infinity, all
this
that goes away.
definition of.
And what do we have left?
Riemann.
We have 2n
Okay.
cubed pi cubed over
And this is
6n
called
cubed.
a
What
Riemann
happens at the
sum.
end?
So what we just did there,
They cancel the
Those
2
things we
reduces
wrote
to
out
6.
where
And
we
get
added up
pi
those
cubed
four
over-
rectangles,
Are you kidding me?
is called a Riemann sum. Now, there's a little technicality. A trapezoid is not a Riemann sum. A trapezoid is not a Riemann sum.
Wasn't that the area?
Think R for Riemann,
Wasn't that the
R
exact
for
area?
rectangle.
Pi cubed
R
over
for
3
Riemann,
by
R
the
for
fundamental
rectangle.
theorem? the antiderivative?
Okay,
Absolutely.
Riemann is what
Okay,
I'm talking
what we
about.
just did was added up an infinite
Trapezoid
number of
is still an
rectangles. We used our
approximation technique,
sigma
it's just not a
formulas or
Riemann
summation
sum
formulas that we've had.
technique.
But
All
we
right, what
just
is a
saw-
Riemann sum? All right, let the
Yes.
interval AB be partitioned into n subintervals by
Pretty cool.
n plus 1 points. Now, you know why it says n plus 1?
Unlike the definition of the derivative, which I made you do on multiple homework
When
problems.
we divided
And
into
then
4
on
subintervals,
quiz
we had to use 5
where you're
points,
not
right?
gonna go through this.
So, we can't
You're gonna
call it
use
x1,
summation
x2,
formulas,
x3,
you're gonna use
x4.
summation. Now, on the
If we're
homework,
gonna divide it into 4
it actually
subintervals, we gotta
does
start with
build up to
x0.
this
So our
in
first,
much the same way.
so our-
There's gonna be some
so
problems
A,
where
our
they're gonna
left
give
edge,
you a
we're gonna
circle
call
like
x
this,
sub
and they're gonna
0,
have you
and
expand
then
it
x
out.
sub 1,
Then there's gonna be
and
some
then x
homework
sub
problems
2,
where they're gonna
then
say,
x sub 3,
okay,
and then
they're
so
gonna
on that
give you
last
this
example
right
we had, we
here.
had those
They're
5
gonna give you
points.
something that just
We would
looks
call
like
them x
this.
sub
Everybody
0,
up here
x
saying,
sub 1,
they're gonna
x
give you
sub
some
2,
problems
x
that
sub
look
3,
like
and x
this,
sub
and
4.
they're gonna
So
say,
that way our
find the limit
last
as n
one,
goes to
if we're
infinity.
doing 4
So then they're
subintervals,
just
our
wanting you to
last
do
one
that
is x
last
sub
step
4.
we did,
That
which
makes
is just
sense.
high powers dominant.
So the B
Okay,
is gonna
and
be
then
x sub
the very
n.
last homework problems, they're gonna
And,
give you something like this,
How many years have I got?
and out in front of it, they're gonna put
This should
limit
be x n plus 1.
as n goes to infinity
Should.
like that, and that's all
The
they
one
want you to do.
before
All they want
x
you
sub
to do
n
is
should
write it
be-
out here, then write it so you can
X
use
sub
your
n
summation
minus.
formula, and then do
Like if that's gonna be x sub 10, then this would be
limit
x
as
sub
n goes to infinity. So when you get to the very
So x
last
sub
homework
1
problem,
is
when
to
it-
the left of x sub,
looking kinda
x sub
hard,
0 is to
kinda
the left
bizarre,
of x sub
it's just
1 is to
this
the left of x sub 2,
last
da da
bit
da.
right here is all.
Is the left of x sub 9 is to the left of x sub 10, and
All right,
then
so-
b right inch.
You're ready. The formal
Okay, so that's all that means, it's just a
Um,
bunch of language
definite
mumbo jumbo, right? That's just how we're gonna
the
divide it.
formal
This is the
definition of a
terminology.
definite integral.
All right. Let delta x sub I be the width of the ith subinterval. So delta x1 would be the width of the first subinterval, and delta x2 would be the width of the second subinterval, and delta x3 would be the width of the
The
third
exact
subinterval.
area,
And
that's
so
what
forth.
definite
Now,
integral is.
you might be
It's the
saying, well,
exact area.
why do
under
you
the
need
curve.
different delta x? Well, you don't have to have the same width.
The exact area under the curve
99%
is
of the time we're gonna do.
equal to, and if you want to just
Almost
put this in common
We're gonna
sense
divide it
language,
up evenly. So
it's
if we got a
adding
width
up
of
and
4
you
and we
get
wanna
a
do
number
4
of
subintervals, they're all
now
gonna
we
be
have
1
to be
1.
a little more
If we got a width of
specific
4
than
and we
that.
wanna do 10
Be
subintervals,
technical,
they're
we'll
all
talk
gonna
about
be
that tomorrow.
4
But it's
10.
adding
Right.
up an infinite
0.4.
number of rectangles.
Wow.
Now that makes sense, I
Okay.
think,
So,
so all the stuff we've done.
Almost
going
always,
forward,
we're just, so
that
delta
the more
x would just
rectangles
be
you
a
have, the more accurate
and
you'll
it'll be
be, so
equal
doesn't it make
across.
sense?
But
if
it doesn't
you
have
add
to.
up an infinite number of
Doesn't
them?
have to be. You
You
could have
could
one
actually
rectangle be this wide and
Get
one
the
be
exact
wide.
area, and that's what we just kind of showed right
Now, where
there.
that would really come into place in the
Important-
table of values.
several important
If you
things
didn't
to
have
see.
a graph or an equation,
Okay.
maybe you only have a
First of
table.
all, that the integral's
You
connected
can't
to a
control
sigma, and
how
talk about
wide
those
your
sigma
interval is for
properties
your
that were the
table
same as
value.
the integral.
Maybe you have a value at 2 and then at 5
The other
and then
thing
at
I wanna
9 and then
point
it's
your
at 10,
attention to
right?
is
Maybe
remember
you
what
got
we
a
talked
3
about
wide,
this
you
DX?
got 5 wide, you don't know.
Being just kind of hanging out there,
Okay.
it just means with respect
So
to.
they don't have.
What we should have
So delta x, basically that
Due
just say
respect
delta x is.
for the DX.
Within each
It actually means
subinterval,
something, it comes from what?
let C sub I be
Look at
the
this.
sampling point. In other
Doesn't
words,
that look like
that's the point
inside
we're gonna
the
plug
integral
into the
itself
function
right
to get
there?
our height.
What is this?
So sometimes
The height of
C
the
sub I
rectangle.
will
What
be
is
our
this?
left edge.
The width, what happens
And
to the width of
sometimes
the
C
rectangle?
sub I
if you
would
have
be
a
our right
number of them?
And sometimes C sub I
We
would
would
be our
have to
midpoint.
go towards.
But it wouldn't have to be
It would
just
have to
those three.
essentially disappear.
We could pick it
You have
anywhere.
Infinite number of rectangles.
You know what I
the
mean?
width would actually
We could pick
disappear.
any point in
And
the
so it does, and that's
subinterval,
why
go
your
up to
integral
the
just really
curve
has
and
no
draw a
value.
rectangle there.
This really
Does that make
has
sense?
no,
We can draw one at the left
it's
edge, we
just
can draw
this
one at
view,
the right
and
edge, we
it's
can draw one at
because
the midpoint.
It kind of
We
disappears.
could draw one somewhere
Now,
else in
the
it.
DX is the width.
Okay, now if you turn to your
Matter of
book,
fact, we can now appreciate in
to
another way
page
why would be
351.
the integral of
if you look at
miles
the
per
bottom
hour,
of
you
page
get miles.
351, you'll see what I'm
Because
talking
what would be the, if you were doing a miles per hour graph, what would be the units on your delta
Look at
x?
the bottom
What would be the units on your width?
of page 351,
What would be the units on your rectangle width?
and maybe I have that page.
It'd be hours. And so when you do an integral that's miles per hour, what you're really doing in a sense is you're adding up rectangles that are miles per hour times hours. So from this point forward, we're gonna think of the integral in a new way, an additional way. Yeah, we're gonna think of the integral as area.
You see those rectangles there? See how some are fat, some are
There's a reason
skinny,
it looks like an S,
right?
like the
So they're all
other
different
sigma,
widths.
right?
And you
That's
see how,
a
like,
connection.
the
It's
first
some.
rectangle looks like
We're
it's
gonna
about
now
at the
think of
midpoint.
this integral as an adder.
See how the
It's
second
adding up a
rectangle
bunch of
looks like the
rectangular
height's right
areas
about
and
at the
put a
midpoint.
number of
You see
rectangular
that?
areas. So when we,
Well, what about
a
the
great
third rectangle?
quiz question would be, explain why
Kinda at the
this
right
is
edge.
the definition of the
The fourth
definition.
rectangle's kind of at
It's
the right
because
edge.
This is a
The
rectangle
next
height,
one's
this is a
kind of in
rectangle
the
width.
middle
You
again.
multiply those, you get a
The last
rectangle
one's
area.
kind of in the
The
middle,
sigma
but going
adds up
past the
n of
middle,
them,
you know what I
and this
mean?
tells you to add up how
But
many.
that's still a Riemann sum.
and
That's
then put a
6
number. And if you add
rectangles,
up an infinite number of
approximating that
rectangle
area.
areas, you
Right,
get
so-
the area under the curve.
right?
Okay.
We don't usually do
One
that,
more.
but
Just
it could be. So that's what all
Okay,
this is
LH
about.
packet, this is the
All
old
right.
LH packet. Now,
This
remember
sum
the one
right
that
here,
we first did, page 289, but the
Oh,
front
and
was
S sub n.
279, it had all those sigmas on
S
it.
for
So
sum,
this is that
N
packet that
for-
the front page.
N is how many
has a bunch of
subintervals we
sigmas
have,
on it.
right? So an
We're gonna
L4
do-
would, N would be 4. So what do you got? You
1
got your
through 8.
height at your first sampling point,
9
so F
through
of
33
C1,
odd.
that's gonna be your height at your first
On
sampling
that
point, times delta x1, that's your width. Well, what's height times width?
Okay?
It's area. So this is the area of your first rectangle, plus the area of your second rectangle, plus the area of your third rectangle, plus dot, 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 and then the area of your last rectangle. So that, what that is right there is exactly what we just got doing on number 17. We did 3 of them that were Riemann sums. We did L4, we did R4, we did M4, and ours looked just like this. We had f of -2 times 1, we had f of -1 times 1, we had f of 0 times 1, we had f of 1 times 1. We were writing out a Riemann sum, is what we were doing. Okay? So, this sum is called a Riemann sum for f on the interval AB. So anytime we do a height times width, height times width, height times width, R for Riemann, R for rectangle. Riemann sum is just adding up rectangle areas, that's all it is. A Riemann sum is just adding up rectangle areas. A lot of fancy language, but it's just saying that the Riemann sum is when you add up rectangle areas.
So what's the dimension? You don't know. There, we're gonna look up our